Hello everyone, this is Vibhaas Srivastava and today we'll be discussing the TLE 31 sheet solutions for the 1600 rated problem, triangle coloring. So let's quickly just pull up the CP31 sheet and let's open up this problem. Right, so let's go ahead and read the problem now. You're given an undirected graph consisting of n vertices and n edges where n is divisible by 6. Each edge has a weight which is a positive integer greater than 0. The graph has the following structure. It is split into n by 3 triples of vertices. The first triple consisting of vertices 1, 2, 3. The second triple consisting of vertices 4, 5, 6, and so on. So basically every three groups of 3 are connected. Right, so they all are connected by an edge and there are no edges between vertices from different triples. So we can just look at the diagram, right? So 1, 2, 3 are connected. Similarly 4, 5, and 6 are connected. 7, 8, and 9 are connected. These components are interconnected with each other. Okay, you have to paint the vertices of this graph into two colors, red and blue. Each vertex must have exactly one color, and there should be exactly n by 2 red vertex and n by 2 blue vertex. The coloring is called valid if it meets these constraints. The weight of the coloring is the sum of weights of edges connecting two vertices with different colors. Let W be the maximum possible weight of a valid coloring. Calculate the number of valid colorings with the weight W and print it modulo 998, whatever the number is given here. Right? So, okay. So basically we just need to find how many ways we can color this into red and blue, and exactly n by 2 should be red, exactly n by 2 should be blue. And also it should have the number, we should calculate the number of ways to achieve a weight W, which is the maximum possible weight of a valid coloring. Okay, so let's see and how we can do this. Okay, so the question says basically we are given a graph with n vertex where n is divisible by 6. Okay, so pay attention, in the constraint is given that n is divisible by 6, so n divisible by 6 right? And what we need to do is every three vertices are colored. Three vertices are connected, so we have a structure like this, right? A bunch of like triangles, and let's say we have these many triangles, right? And now we need to color half the vertices red and half the vertices blue. Okay, so half the vertices red, let's say this is red, this is red, this is red, this is red, and let's say these two are red. Now the other half can be blue, so these are blue, this is blue, this is blue, and so this is a valid way of coloring it into red and blue vertices. Now so basically the weight of coloring is the sum of weight of edges connecting two vertices of different colors. So we need to find the vertices of different colors. Which vertex can be different colors? One option is these, right? These are vertex of different color. Similarly, these are vertex of different color, right? As you can see here and here, all the vertex are same color, so none of the edges weights will be counted. All right, so let's say this is the weight 1, this is the weight 2. Similarly, this is the weight 1 and this is weight 3, weight 4, right? And these are the weights which will be summed up for the total weight. Now we need to find W, which is the maximum possible weight of a valid coloring, and then we need to calculate the number of valid colorings with weight W, and that's what we need to print. So let's make some observations here. The first thing to note, obviously, before starting the problem, is what is the expected time complexity. So we can see that the expected time complexity is big O of n or big O of n log n. That's the roughly expected time complexity, since n goes up to 2 times 10 power 5, right? Okay, so now we basically need to do a counting problem. So we need to use some ideas of combinatorics and we need to see how we can break this problem down. So the first thing, let's try to see what are the possible colorings for a given triangle, right? So all these triangles look independent, so we'll try to see the possible colorings for a triangle and analyze what happens. So colorings of a triangle, right? Triangle. Okay, so let me just make any random triangle, let's say here, and let's put some weights. Let's put 5, 8, and 10, right? Now in there are two cases where all the colors are same, so it's all red or all blue. Now in this case this will not add to the sum, correct? If all are red, or all are blue, then this is not going to add to the sum, right? And we want to maximize the sum. We want to, if you read here, it's saying we need to find the maximum possible weight or maximum possible sum of the edges. So that's why this is not a good idea. What we should try is we should try to keep some red and some blue, right? So now what happens if we keep one red and two blue? If we keep one red and two blue, then the edges which are connected to the red, like this one and this one, they will get summed up to the weight. So for example, if this was the arrangement, it would be 15. The total weight this would add would be 15, right? Let us see a similar example. If this was blue and these two were red, then again nothing changes. Again the sum will be added as 15, right? So basically the only option we have is one red, two blue, one red, two blue, right? Or two red, one blue. That these are the options which we have. And in both cases, two edges will be added, right? So basically what is happening is by coloring them red and blue, essentially what we're doing is we are saying we can add the weight of any two chosen edges. Add the weight of any two chosen edges. Any two chosen edges. All right. So, and what would we choose? So in the way we want to maximize, obviously we'll choose the largest two edge weights. So here's one edge weight and here's one edge weight, and these are the largest two. 5 is the smallest one, right? So what we're going to do is we'll color, let's say this red, and we'll color these two blue. So then 5 will get excluded and 10 and 8 can be taken together, right? And they can be adding to the sum. They will contribute a total value of 18 to the sum. Okay. So now this is the correct way we need to sum it. Or basically, if you view it in another way, we are excluding one edge. We are excluding exactly one edge, and that is the smallest weight edge. Okay, we are excluding exactly one edge, smallest weight edge, right? So why are we choosing the smallest weight edge to include? Because that's the one which is giving us the minimum benefit to our sum. Okay, right? So that's what basically, and this will give us the number of ways to color a given triangle. All right, so we know that each triangle is either two blue, one red, two blue, one red, or it is two red, one blue, right? We know this already. So, and both the cases are similar. They don't change anything, right? They don't change anything. Only thing is just the colors change, but the excluded edge remains the same, right? Excluded edge remains the same. Okay, so now let's have a few examples. So one example is, let's say we have different values like last time. So we have 5, 8, 10, right? In this case, the excluded edge should be this one, right? This is the edge we should exclude. Now, what if, let's say our triangle looked something like this, all right? If we had a triangle which looks something like this, 5, 5, 5. So all are the same. It doesn't matter how we color as long as we just pick any two edges, right? As long as we get any two edges to add to the sum, it doesn't matter which edges we pick or which edges we exclude. So basically what we can say is we get three choices here. Okay, we get three choices. Either we exclude this edge, we exclude this edge, or we exclude this edge. So there are three choices over here. Now what if we had, let's say 5, 10 and 5. Now in this case again we have two choices. We have two choices because we can either exclude this edge or exclude this edge. So now let us summarize our results. So in the case of a triangle with two colors of one type and one color of the other type, basically in every triangle, let us have the edge weights as A1, A2, A3. Okay, A1, A2, A3. And what happens if A1 is less than A2? Let's say basically something like this, right? So we have a case where A1 is the smallest, is less than A1, which is less than equal to A3, right? So for example, the 5, 8, 10 type of case. So now, or we can write it in such a way, case 1, there is a unique minimum weight edge. There is unique minimum weight edge. Minimum weight edge. Then we have to only and only exclude that one. We can only exclude that one. So what we can write is, in this case, only one way to color this triangle, right? Only one way to color this triangle. Color this triangle. Okay. Now, what if there were two minimum weightage? Then we can choose either this one or that one. So then there will be two ways, right? There is two minimum weightage. There is two minimum weightage. Weight edges. Then there will be two ways, right? There will be two ways. Two ways to color this triangle, right? This is the second case which I showed. And similarly, if they are all three are equal, or there are three different minimums, right? Case 3, three minimums. In other words, all three are equal. All three equal. Then there will be three ways to color, right? There will be three ways to color. Okay. So this much observation we have done. So this is the first idea, or observation 1. Okay. Observation 1. And yeah. Now what else do we need to observe? One more key fact we need to observe is that these choices are independent. Okay. These choices are independent for each triangle. These choices are independent for each triangle. For each triangle. So basically what happens is we can just directly multiply, since we have several independent choices. So in that case, multiplication rule of combinatorics will apply, right? And we can just directly multiply the number of choices. So for example, if we had like 5 triangles in a test case, like this, like this, like this, like this, let's say something like this, okay? And let's say in the first triangle we had only one way to choose minimum. In the second triangle we had two ways to choose minimum. In third triangle we had three ways to choose minimum, and again maybe two ways and one way, right? So then we can say that there's only one way to color over here. There's two ways to color over here, three ways here, two ways here, and one way here. So we can multiply that to find the total number of ways to find which is the minimum weightage that we are choosing. Okay, so we can set this to our answer. Fine. Now the only thing which remains is to figure out which ones will be having two reds and which one will be having one blue, and similarly which one will having two blue and one red, right? So let's say this one has one red, and then this has two blues, something like this, and similarly this one will be, let's say, a blue, and this one will be two reds, right? Something like that, and so on and so forth. We can fill up the colors, right? And what we know is there will be equal numbers, since we want n by 2 red, n by 2 blue, and n is divisible by 6. So we will have equal number of red blue blue, red blue blue versus blue blue red red, right? So equal number. So we need to choose basically n by 2 or maybe half of these triangles for coloring red and half of these triangles coloring blue. So the number of ways to choose this will be how much? So let's just write it down. Number of triangles is equal to n by 3. So basically number of triangles with two reds, triangles with two reds, one blue, that is going to be equal to n by 3 divided by 2, which is n by 6, right? So how do we choose these triangles? How do we choose these triangles? We simply do total number of choices, choose how many choices we're choosing, right? So that will be simply n by 3, choose n by 2, n by 6, right? So this is the quantity we need, and this quantity we can simply write as another way to write is like this, right? N by 3 choose n by 6. So we can write it as in factorial form, using the factorial formula. We can write n by 3 and n by 3 minus 1, n by 3 minus 2, so on and so forth till we reach n by 6 plus 1, right? Till here. And now here we can divide by n by 6, n by 6 minus 1, so on until we reach 1, right? So basically this is the quantity, and now if we multiply the number of ways to choose within each triangle versus the global way to choose the color of the triangle, right? We will get our final answer because that's the only choices we have, right? So again, multiplication rule of combinatorics. So let's just write down the final answer. Final answer is equal to first the product of the number of minimums, right? So product for all triangle x, number of minimum of x, number of minimums of x, right? Minimum edges. This multiplied by choosing the colors, so that will simply be n choose 3, sorry, n divided by 3 choose n divided by 6, right? So this is the final answer, simple mathematical formula for the answer. Yeah, how do we implement this? So this part is directly implementable. We just need to do modular multiplication, right? We need to be careful. Now for this, we need to do the factorial formula. We need to use the factorial formula and modular division, right? Use factorial formula of NCR and mod division, right? And if you know basic mod division, you'll be able to easily calculate it. If you don't know mod division, you can go look it up. It's a pretty common idea for combinatorics problems, right? And then the overall time complexity for this will be simply big O of n, right? Overall TC will be simply big O of n, as well as the memory complexity. We're not using any extra memory, but we're obviously taking input. So overall memory complexity will be again big O of n, right? So let's just have a look at the code. Yeah, so this is some helper functions to do modular arithmetic. So this just adds, subtracts, multiply, and inverse is for the division, right? So when you want to divide in modular arithmetic, what do? Basically, if you want the value of a divided by b mod m, then that is the same as a times b inverse mod m, right? So that's why we need inverse over here, so that we can do the division while calculating the factorial, okay? And that's why we have all these helper functions for mod. Okay, so now let's look at the code. It's not that complicated. We set our ans variable to 1. Then from I equals 1, j equals n by 3, we go to I less than equal to n by 6, right? So we're trying to calculate this factorial. We set I equals this, right? We're setting I equals this and j like this. And what we're going to do is we're going to iterate step by step this way. And here also we're going to iterate step by step this way. And we're going to do modular division, right? And that's why we're doing I plus plus j minus minus. And this ensures that, you know, the factors don't get lost anywhere. Like as we go on from 1 to 2, it ensures there's a factor of 2 always, etc, etc. So we're just doing modular division over here. So this will calculate the value. This loop calculates the value in answer of n by 3 choose n by 6, right? It calculates this value and stores it in the answer. Now we need to actually take the input, right? Actually, to be honest, since we don't even need to store the input, we just need to store chunks of 3 each time. The overall memory complexity will only be big O of 1, right? So let me just make a quick correction. The memory complexity is just big O of 1. We don't actually need to store the values for this, right? But if you're storing the values, it will be big O of n. So let me just write the memory complexity as big O of 1. Okay. So for every 3 values, we take in the value. And if we know that we have just taken 3 values, right? So I mod 3 equals 2. We can sort the last 3 values which we have taken in. And what we can do is we can check if which one is the smallest one. And like basically I'm setting multiplier equals m, right? So multiplier means the number of minimums, right? Multiplier number of minimums is 1. Then if it's equal to v1, then number of minimums increases. It's equal to v2, again number of minimum increases, right? Because one value is equal to minimum and similarly the other value is also equal to the minimum, right? And then finally we can multiply the answer with that value m, right? So if there are 3 minimums, we multiply the answer by 3. If there are 2 minimums, we multiply the answer by 2. If this is 1 minimum, we multiply the answer by 1, right? And this gives us the same exact thing we're calculating. So first we're calculating this part and then we're calculating this part, right? And now finally, once we're done, we can simply print the answer. So very clean and efficient code. O of n time complexity, O of 1 memory complexity. The topics used here are combinatorics. Topics used are basic combinatorics and modular math, right? Combinatorics, mod math slash inverse, right? Inverse idea. So that's about it. Pretty straightforward question, not much to comment. If you couldn't get it, then do practice more combinatorics, more inverse mod matrix operations. And yeah, that's about it. Thank you for watching. Hope you learned something and see you in the next solution.